Lesson 7 demo. In this class, we find relative and absolute extrema for in-context problems. 1. For the function pictured, identify the x-coordinates of all local maxima and minima. So we're looking for points that are higher than any point nearby. So for example, there's a local max, and there's a local min, and another local max, and another local min. We're not saying those are the highest or lowest points anywhere on the graph. For example, this point has points that are lower than it, like over here and over here, but this point is lower than all the points that are nearby, so if we just want the x-coordinates, I'm just reading them off from the x-axis down. We've got B and D and F and H. B and F were the local maxes, and D and H were local mins. Number 2, notice that at each of the local extrema of the above graph, extrema is the set of all maxima and minima, at every single one of those points, the tangent line is horizontal, which makes sense, right? Like at every one of these points, the behavior of the graph changes from increasing to decreasing or vice versa, decreasing to increasing. Number 3, it is possible to have a relative extreme point where the tangent line is not flat. At the local min in this graph pictured at right, the function is not differentiable because of the corner, but still, this is a local min because it is lower than any point that is nearby. So it turns out there's exactly 2 kinds of points we need to look for, we need to examine when we're looking for local maxes and local mins. They are the points where the graph is horizontal, like in this first picture, and there are places where the derivative doesn't exist, like in the second picture. Number 4, we summarize our observations from above in the following theorem, which is proved in your book. It's called Fermat's theorem. If f has a local max or min at c, c is the x value, then either f prime of c is 0 or f prime of c does not exist. Either the derivative is 0 or the derivative does not exist. We call c a critical number if its derivative is 0 or if the derivative does not exist. So the above theorem tells us the only place that relative extrema may occur is at critical numbers. The only candidates for local maxes and mins are critical numbers. Okay, number 6, it says, go back to the first graph in this section, identify the x-coordinates of all global maxes and mins on the interval a to j. That's a closed interval. From a to j, we want the global maxes and mins. So a is right here, and j is way over here, and I'm only looking between those spots. And here, I'm not looking for points that are just merely higher than the nearby points or lower than the nearby points. I want to find the absolute highest point anywhere on this interval and the absolute lowest point anywhere on this interval. Okay, so looking for the highest point on this interval, I actually think it happens at j. This point way up here is higher than any other point on this graph in this interval. And how about the absolute lowest point? Well, it's not at the point A. It's not there because, for example, here is a point that's lower than A. So where is it? Well, is it here? Well, that's a pretty low point, but that point isn't as low as this one. So I think this is the winner right here. That point is lower than any other point on this graph between A and J. Now you can argue and you could say, hey, but there's a point over here that's lower. Yeah, I agree with you, but that point over there is not in between A and J. This one is too small, right? It's out here to the left of A, so it's just not in the ballpark. So in this case, we had an absolute max at J and an absolute min at D. Make sure you see that. Okay, so I said absolute. It's a synonym for global. Global max at J, and then a global min at x equals D. So let's analyze why those 2 points were special. So D was special because it's a critical point, right? It's a place where the derivative is 0, where the tangent line or the graph is flat. J is only special artificially. J is special because it happened that was the end of the interval, right? There's nothing special about J. If you let me go just a little bit to the right of J, I find points that are higher than the one at J. So D, I would say, is fundamentally special for this graph. It is called a critical point. J is artificially special only because it's an endpoint. You pick a different interval where J is not an endpoint, then J is not going to be the answer to any of these global max or min questions. So that gives us a procedure here in number 7 to find the absolute extrema That's the absolute max and absolute min of a continuous function on a closed interval, just like the a to j we just had. Just evaluate the function at each of the critical points and at the endpoints and grab the highest and lowest values. Sounds tough, but it's really not. It's a pretty straightforward process. You're going to get a lot of practice with it. Number 8, without using a graph, find the absolute extrema of this function right here on the interval -2 to 6. Okay, so what are we supposed to do? Well, first thing we need is to find the critical points. And the critical points happen when the derivative is 0 or when the derivative does not exist. So the first step is to calculate the derivative using our shortcuts now. So I see sums and differences. That makes me happy. 3 comes down, multiplies by the 2, gives me 6. X to the subtract 1, that's a 2 up there. Minus 2 comes down, multiplies by the 3, gives me another 6. X to the subtract 1 from the power to get a power of 1. I won't write that. Minus 72x, that's a special case. That's just the constant 72. Plus 5, plus constants disappear when you take derivatives. I won't write the plus 0. Okay, we want to take this derivative and set it equal to the magic number 0. Taking a derivative and setting it equal to 0 is something that is going to come up over and over again this semester. So in order to solve this thing without a calculator, I guess we got to either use the quadratic formula or factor. We're going to at first at least factor out the greatest common factor, which looks like it's a 6 going into everything. So x squared minus x minus 12. And then this thing in the parentheses actually factors further. So I see x minus 4 and x plus 3. And then we set each of the parentheses equal to 0. And we get 2 critical points, x equals 4, x equals -3. 2 quick notes. Some folks don't like the fact that we ignored the x equals 6. So, okay, don't ignore it. Set that thing equal to 0 as well. And then say this does not have any solutions. So x equals 4 and x equals -3 are the only critical points. Also, the definition of critical point says it's where the derivative is 0, but also where the derivative is not defined. So the question is, are there any points, any values of x that make this thing undefined? Well, no. I mean, to make something undefined, you need to divide by 0, and there's no division at all here. So those are indeed all of the critical points. And now we're going to make a table. Here it is. We've got x. We've got something over here. We've got f of x. We're going to put into this table the critical points. We've discovered they are 4 and -3. 4 and -3 critical points, and also the endpoints. I would say 4 and -3 are really important for this graph, but artificially important are -2 and 6. So let's plug those in here as well. -2, 6 endpoints. And the last thing before we do any evaluating, if either of the critical points is not in between your endpoints, then you can toss it out, right? The only thing we care about is what's between -2 and 6. Is 4 in that interval? Yeah, it is. Is -3 in that interval? No, it's actually not. So don't even need to mess around with -3. Not in interval. So we're going to plug all of these things in. Now it is tempting to plug them into the derivative. That is not what we're doing here. We are grabbing the highest and lowest values by evaluating the function itself, the original function. So let's plug 4 and -2 and 6 all into the original f of x. So here we go. When we plug 4 in, so I'm actually going to use a calculator to help me on this, just to speed things up. So here we go. Because I'm doing 3 function calls here, I'm just going to type the function in one time. 2x to the third minus 3x to the second minus 72x plus 5. Second table set, I want it to ask me the values I'm interested in, and the ones I want are 4 and -2 and 6. So I think that's the quickest way to use the calculator to do these 3 function calls. So -203, 121, and -103. Okay, and I claim that the absolute maximum on this interval is wherever the y values here, whichever y value is the highest one. And so I can see that right here, 121 is the biggest number. of that collection of 3 y values. So this right here, absolute max. Let's try that again. Absolute max, -2, 121. Okay, that's good. And then the absolute min occurs wherever the smallest y value is. So -203 compared to -103, so the smaller one is -203. So this, oh goodness. So this tells me that the absolute min is at 4, -203, just like that. And so we can take a look at the graph of this function. I've already typed it into the y equals, but let's think about the window. Well, all right, let's do the standard window first. Let's see what that looks like. Okay, so it goes up there, way off the graph. I saw something here, it looks like 3 vertical lines. I get really no good information about the graph of this function on this window, but hey, we just did a lot of work over here, and that's gonna tell us what a great window is. So check this out, -2 to 6, that's the x's, -2 to 6. And then the y's have to include -203 at the bottom. So I don't know, how about like -205? And then it's got to get all the way up to 121. So how about 125? And then, I don't know, let's go by tens. And this should be a very nice window for the graph of this function. It looked like it was going to go off the screen, but it didn't, came back. And we can see on this particular interval, the absolute maximum is way over here at -2. That's the start of this function, start of the interval. And then the min happens right there at x equals 4, which is again what we predicted. Now 6 was at -103. That was negative, but it wasn't as negative as this one. So that's why we picked this guy. So the critical point was one winner, and the end point was the other winner. Just for kicks, let's see what's happening at -3 here, because we didn't include that in our windows. How about we go to like -5, see what that looks like. All right, so it went slightly off the screen. I'm going to stop it because I want to see that. Just a shortcut there. Push on, it'll stop the graph. You don't have to wait for it. So I guess I want to go just a little bit higher here. How about 150? Let's see if that captures it. There we go. So -3 is indeed a critical point. -3 is a higher point than the one that we picked. We picked -2, right? -3 is higher than a -2, but -3 was not fair game, was not inside of our interval. So number 7, again, real standard procedure. Make sure you understand the process. 9. Here's our first of many optimization problems. A math book is to contain 36 square inches of printed matter per page with margins of 1 inch along the sides and 1.5 inches along the top and bottom. Find the dimensions of the page that will require the minimum amount of paper and find the minimum amount of paper. We'll use our first sign chart at the end, and then there's a hint about L and W. Okay, so let's draw a diagram. So we've got this rectangle, and inside of this rectangle is supposed to be an inner square where we're actually going to have the print. And what it says is that there's supposed to be margins of 1 inch along the sides. So I'll put that in here. Here to here is 1 inch. Here to here is 1 inch. And then 1.5 inches top and bottom. So not quite to scale. That's okay. 1.5 inches there and there as well. And then the printed matter is this stuff in here, and then just blank space around the outsides. That's the margin. And so it says that we want to find the dimensions of the page that will require the minimum amount of paper, So let's be clear. We're trying to get 36 square inches of printed matter. So for example, one possible way to get 36 would be like a 9x4. And then you add your inch along the top, 1.5 inches around the sides, etc. But there's lots of ways to get 36, right? Maybe I go a little bit taller. I'll do like a 12 and a 3, 12, 3, something like that. So taller but narrower, but then we still have to go like 1.5 inches up and then 1 inch around the side, 1.5 inches down. I really doubt that the amount of paper in each of the 2 big rectangles I just drew is equal to each other, right? Like the paper, not just the printed stuff. But the paper is that much there, and then this much here. It's unlikely that they're exactly the same as each other. So probably, you know, like there's some magical point, magical dimensions of the inner part that will get us the least amount of paper altogether. I can go really extreme here. I'll draw one last one and then we'll stop. Suppose that the inner part was 36 inches by 1 inch. So we're just going to go 1 inch on the top and then really long off the bottom of my screen there, and then 36 inches. Now that's still 36 square inches, but where I'm going to eat it is the 1.5 on the top and bottom and the 1 on the side. That's going to use an awful lot of paper. And so I don't think 36 by 1 is going to be the optimal way to minimize the amount of paper used. So let's see if we can figure out how to minimize the amount of paper. Okay, so the hint is that we are going to let L and W be the length and width of the printed part, not the outside page, but just the inner page. And so we'll say that W is that part there, and then L is this part over here. So L there, W there. So let's go ahead and use our definitions. In fact, we don't need to, but it says it there. It says let L be the length and let W be the width. Well, why don't we do it? Good habits. L equal the length in inches and W equal width in inches. Okay, so we've got quantity words and unit words, length in inches, width and inches. Okay, so here's a fact. We know that the printed matter is supposed to be 36 square inches. So we know that L times W, because that's the area of the inner rectangle, has to be 36, right? I don't know what I'm going to do with that, nothing at the moment, but it is a fact that is going to help us down the road. So then it says find the dimensions of the page that will minimize, give the minimum amount of paper. So apparently we need an expression for the amount of paper, not just the printed part, but the entire thing, the area of the whole page. Okay, so I know that the area of the whole page is the length of the whole page times the width of the whole page. So let's take a look. The length of the whole page, that's from there all the way down to there. What is the length of that whole page? Well, a bunch of it is L, right? L is like between those two red hash marks. But then above the top hash mark is a 1.5, and below the bottom hash mark is another 1.5. And so the entire length of red is L plus a couple of 1.5s, or L plus 3. Okay, so hopefully that will help unlock the door to the width of the entire piece of paper. I have enough colors. All right, how about this thing right here? So from there to there, that's called W, but then there's a 1 inch to the left and another 1 inch to the right. So I count W plus 2 right here. Okay, so this right here is the expression that represents the total amount of paper we're using, the number of square inches of paper, and we're trying to minimize it. We're trying to make it as small as possible. Well, the bad news is the right-hand side has two variables. It's got L and W. And when you take Calculus 3, that's not going to be a problem for you. You'll be able to deal with functions of many input variables. But in Calculus 1, we can only handle one input variable. So what we need to do is replace either L or W with a function in terms of the other letter. And so that's where we come back to that blue equation. We're going to solve this thing for either letter. It doesn't matter which one. I'll solve for W, so divide both sides by L. And then we're going to substitute that into our area equation. So the L I'm happy with, but that W is about to change to a 36 over L. Okay, so now let's take a look at this formula. This is better for us because it's a function involving only one letter. We know that in order to find the minimum point on a graph, we're probably looking for places where the graph is either undefined, where the derivative is either undefined or where the derivative is 0. So I need to take a derivative of this thing, but I can't in its current form because it involves multiplication of two functions. We don't yet have a product rule for taking a derivative of the product of two functions, so we just have to distribute. So we're foiling here. First times first, outers, inners, and last. And so the first times the first is L times 36 over L, that's just 36, plus the outers, that's 2L, plus the inners, 3 times 36, I think is 108, divided by L, and then plus the last. So that's the formula for the area. Let's go ahead and clean that up. We'll just smush together the 36 and 6. That's 42 plus 2L plus 108 over L. Now it is in a good form for us to take a derivative. So let's use our good notation. A prime equals, okay, the derivative of 42 is 0. I won't write it. The derivative of plus 2L, that's just 2. The derivative of 108 over L, that's one of our special cases, constant over x, becomes negative the constant over x squared. So negative 108 over L squared. And that's it. Because we know our derivatives really well in a couple of special cases, this derivative was a piece of cake. Okay, now we're looking for critical points. That happens where the derivative is 0 and where the derivative is undefined. We're going to solve this equation in a second, but I will point out there is one spot where this derivative is undefined, and that's at L equals 0. But the fact is L equals 0 doesn't make any sense in the context of this problem. You can't have a 0 length. The length has to be positive. So that critical point is like considered and then ignored. But we are going to get at least one answer out of this equation. So we'll solve, add the 108 over L squared to both sides. I'll multiply both sides by L squared, divide by 2, and then take a square root. Technically, there are two answers. It's square root of 54, but then also negative square root 54. But again, a negative length doesn't have any meaning, just like a 0 length doesn't have any meaning in this problem. So that negative square root of 54 is technically a critical number, and then it gets ignored. Okay, so we're going to do a sign test, the very first sign test, the first of many sign tests this semester. Here we go. You're going to put that critical number on the page, square root of 54. You could simplify it if you want. Ultimately, I think, yeah, we'll probably get a simplified exact answer. In fact, why don't we just go to decimal form, make it a little bit friendlier for us. So square root of 54 is what I'm interested in here. Okay, so that's around 7.3. Okay, so roughly 7.3. So I'll call that 7.3 here. We'll be very friendly. 7.3. Okay, this takes the real number line and cuts it up into two kinds of numbers. There are numbers that are less than 7.3, and there are numbers that are bigger than 7.3. And what we're going to do is also put the 0 on here. This is values of L on this number line. We're putting 0 not because, well, it is a critical point because that's where the function's undefined, but really 0 is the end of values of L that make any kind of sense in this problem. There's no point considering anything less than 0, and frankly, there's no point considering 0 either. Okay, so here's what we're doing. We are going to plug numbers in. I've got two intervals now on my number line. I've got all the stuff in between here, 0 to 7.3, and then I've got all the stuff over here bigger than 7.3. And we're going to plug those numbers into the function that the 7.3 came from. We've got two functions on the board. There's the original A function and there's the derivative. Which one gave rise to this 7.3? This 7.3 came out of a calculation involving the derivative, not the original, right? There's nothing in here that said 7.3. It was this thing equal to 0, which got the 7.3. So we are going to plug numbers into the derivative. We're going to label this number line with A prime. Okay, so we're taking this thing and we're going to plug in a number in between 0 and 7.3. So we're picking a number in here right now. Okay, so for example, I'll pick the number 1, and we're going to plug it into A prime. And when I plug L equals 1 right in here, here's my A prime, and I'm plugging L equals 1 right there. I get 2 minus 108 over 1 squared. Now, I actually don't care what that number is. All I care about is whether that number is positive or negative. So let's look at it again, only paying attention to whether that number is positive or negative. So 2 minus 108 over 1 squared, that's 2 minus 108. That is very much a negative number. And so all I'm going to do is put a negative sign up above. Any number that I had picked between 0 and 7.3, I could have plugged any number in that interval, plug it in for L, and you would get something negative in the derivative. I plugged in 1, but you could have plugged in 2 or 7.28, anything. between 0 and 7.3, you will get a negative value for the derivative. Let's do the same thing now, but to the right of 7.3. I'm going to pick something out here. I don't know, we'll pick like 8 or 10, or how about 100? 100 sounds like it's daunting, but actually I think it's easier than plugging numbers in that are close to 7.3. So let us plug in 100 for L into this expression. So L is 100. 100 squared is 10,000. You don't need to know exactly that it's 10,000, but you should know it's really big. And then you take 108 and you divide it by 10,000 and you get something very close to 0. And then we do 2 minus this number, which is close to 0. And all I care about is that positive or negative. 2 minus something very close to 0 is for sure positive. Any number you pick out there, you're going to get something positive. And so what does this mean to us? Well, it means that the derivative of the a function is negative between 0 and 7.3, and then positive for the rest of the way. And if the derivative is negative, that means we've got downhill sloped lines. Downhill sloped lines. And then the derivative is positive, which means we have uphill sloped lines. And this is the entire collection of interesting things about this particular function. The only point that's interesting is 7.3. And to the left of 7.3, the function is decreasing, and to the right of 7.3, it's increasing. And so I can really see the picture of the graph. I don't know exactly what the graph looks like. It's probably not like a nice parabola or anything like that, but for sure it is down, 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 and then up, up, up. And so what kind of a number are we staring at 7.3? It must be a minimum. And in fact, it is the global minimum. It's the lowest point anywhere on this function. So that is our answer. L equals 7.3 is the min. And I think this thing said find the dimensions maybe of the piece of paper. Let's take a look. It says find the dimensions of the page, so that's the whole paper, and the minimum amount of paper. Okay, let's try it. So L equals 7.3. Let's go ahead and find W. W is given right here. It's 36 divided by L. W is 36 divided by, now 7.3 was our estimate. I'm going to put a square root of 54, and I'll just type it in that form. Again, you can clean that square root of 54 up a little bit and reduce, but I'm just going to decimal land here. 36 divided by second answer. So we'll say about 4.9. And so then the dimensions of the actual page, I'm kind of running out of room here. Remember that the L, we had to add 3 to it, and the W we had to add 2. That'll get us the entire page. So we're adding 3 to the L. So it used to be 7.3, so now it's a 10.3 by, and then we're adding 2 to the W, 4.9, add 2, we get 6.9. And then the area of the page is the product of those two numbers, but I don't need to introduce extra rounding errors, so I'm just going to get an answer that's as close as possible to the right one, whatever my calculator can do. So what we're supposed to do here is take the square root of 54, come on, square root of 54, and then we added 3 to that number, and then we multiplied that by, W was 36 over square root of 54. So again, trying not to introduce any extra rounding here. And then we were supposed to add 2 to that number. So this gives us the dimensions of the entire page. We'll call it around 71.4. Square inches there. Let's see how close we would have gotten if I hadn't typed all that stuff in, but rather just did 10.3 times 6.9. So you can see, I mean, like, you know, introduced like 0.3 square inches of error. I mean, it's not nothing, but it's not the end of the world either. Okay, so here's the required justification that is typical at the end of a max or min problem. Here we go. This is fill in the blanks with the choices or some guidance down below the blank lines. So since something, A or A prime, goes from either positive or negative to positive or negative at a certain point, then one of these functions has a local max or a local min at that point. All right, so let's start with the at the point. So L equals 7.3, that's the winning value. So that goes in these ones. L equals 7.3, L equals 7.3. And did we discover that L equals 7.3 is a max or a min? Well, looking at these blue lines here, it goes down, it goes up. That is a minimum for us. So we have a local min at 7.3. What function has a local min? Is it a or is it a prime? Well, take a look at the sign chart. This was a prime on the sign chart, but the graph, the stuff in blue, was our representation of a. The graph of a is the one that goes down and then up. And so, in fact, it is a that has a local min. So we just have to fill in the rest of this here. It says something goes from either positive to negative or negative to positive. So let's take a look. On the left-hand side was negative, on the right-hand side was positive. So we go from negative to positive. And what function went from negative to positive? Well, the function that we got the negative and the positive from was a prime. It's labeled right there. So that's what goes in this first one. So here's our full sentence. Since a prime goes from negative to positive at L equals 7.3, A has a local min at L equals 7.3. And so we're going to give you the template for some of the problems in the activity. And then I think at some point you just have to write those sentences on your own, but keep using the template. Refer back to this template. Okay, number 10, the ideas behind our sign chart above are formalized in the following theorem. Suppose f is continuous at a critical number x sub 0. If f prime of x is negative immediately to the left of x0 and positive immediately to the right, so I am envisioning that the f function, let's see, it's negative, so that means we're decreasing, and then positive, that means we're increasing. So I'm trying to imagine what the f looks like. Then f has a relative, in this case it is a min at x0. This is your x0 right here. Okay, other side, if f prime is positive to the left, that means that f is increasing, and negative to the right, that means f is decreasing. Then what's going on right there? That then f must have a relative max at x0. And then finally, if f prime has the same sign on both sides of x0, then f has neither a relative max nor a min. So for example, if your sign chart f prime over here, if you had a positive and a positive, that would mean that f was increasing to the left and then flat for just a second and then increasing again. So that means this point right here is neither a max nor a min. Okay, 11 summarizes the two fundamental Calc 1 processes we've seen today. To find relative extrema, take a look at the next part. It says find absolute extrema. So just make sure you're clear on the difference between the two processes. To find relative extrema, you find the critical points and you do a sign test on the derivative function. Relative extrema is critical points and a sign test on the derivative. To find absolute extrema on a closed interval, that's where we make our table, like on the previous page. You evaluate the function at each of the critical points and at the endpoints and identify highest and lowest function values. I will say that that first optimization problem that we did is one of many we're going to do throughout the semester. Optimization problems are notoriously difficult, and it is very early on in our calculus careers together. So expect to struggle a little bit. These problems are tough, but they do get easier with practice.